Hello everyone. Although a little late to be talking about, today I would like to share my experience interning at Sunnybrook Research Institute last summer in August. I was a part of the cardiovascular sector interning at the MRI research group led by Dr. Graham Wright. So my interest in the lab grew from a project my friend and I were working on called Project Heartscope, and the project is a machine learning based initiative, and we'd only really worked with one data set focused on the basic classification of a cardiovascular condition called cardiomegaly based on x-ray scans. But I soon learned about MRIs and their not so recent introduction specifically in this field, and wanted to learn more about how they functioned in a lab and where treatments for CVDs came from. And my manager, Bonnie, aside from being one of the coolest and most humble people I've ever met, was a key individual in my growth milestones in August, as well as my exposure to the world of magnetic resonance imaging in cardiovascular care. So at Sunnybrook, I worked on a fascinating project relating to arrhythmia, and it was specifically catheter tracking for ventricular tachycardia, and it was quite an enlightening experience. So we're going to take it back a notch and look into what arrhythmia is and what particular subtype I was working on, as well as how the heart's electrical system kind of ties into it. So arrhythmia is a cardiovascular condition with irregular or inconsistent patterns of heartbeat. And two primary types focusing on the heart rate speed are tachycardia and bradycardia. Each of them have their own particular subtypes, and the major focus of my project at Sunnybrook was on a subtype of tachycardia called ventricular tachycardia. So, I don't think tachycardia a lot, but tachycardia involves an abnormally fast heart rate greater than 100 beats per minute, and of the many types, ventricular tachycardia originates with messed up electrical signals in the ventricles, which are the lower chambers of the heart. So let's take it back another notch. As we know, the heart's rhythm operates on an electrical signal-based system. The natural pacemaker in our heart, scientifically known as the sinoatrial node, generates an electrical signal that spreads over the atria, which is the top chambers of the heart, and the atria contract simultaneously because of the signal and are followed by the closing of the atrioventricular valves. Then the signals reach the atrioventricular node, and then the signals send nerve signals through the septum, which is like a divider for both sides of the heart, the oxygenated and oxygenated, and it goes through the bundle of His branches when it reaches the apex down the Purkinje fibers, and the ventricles essentially push blood up at that point and contract simultaneously, ultimately followed by the closing of the semilunar valves. So that was a little bit of a lot, but essentially in ventricular tachycardia, the electrical impulses start from the ventricles instead of the sinoatrial node. And as you can imagine, this would kind of mess up the heart's filling with blood before being able to pump it out system. And if the ventricles cannot pump blood well, then the body does not receive adequate oxygenated blood. One method of treatment is called ablation, and it is the idea of using energy to create scars in the heart, which block these kind of messed up signals and are responsible for the rapid heartbeat. And the ablation process requires a tool called a catheter, and it's this specialized tool with sensors that send signals and record the heart's electrical signals. And it plays a crucial role in tracking and locating the key areas for ablation. So the project I worked on focused on utilizing MRI to track catheters, as magnetic resonance imaging allows for clearer soft tissue contrast in comparison to other systems like x-rays. But the problem is viewing the catheter is kind of a struggle. So the project focuses on developing catheter tracking algorithms in an MR setting. So although the greater kind of part of the project was complete, my role ensured focusing on clarity in code, reproducibility in a Windows-based environment, and documentation. So I established the documents in a Windows environment and then enabled basic instructions and ticket files, and worked on the organization of data and code. In the process, I kind of had to learn how to work with Bash, which I'd never done before, in a Linux-based system, which was also kind of new to me. And this involved, again, through the process, generation of graphs in a new environment, research into tools such as Binder and NeuroLibre for improved access and enhanced reproducibility of the project itself. And I could say going through the process of setting up the software, navigating through the varying technical challenges along the way, and ultimately, moving one step closer to reproducibility was, although difficult, a rewarding experience that was topped off with kind of a fun final presentation of my developments. And I believe that beyond being able to set this all up and run through the project's various algorithms and learn about all these kind of complex tools that work together to bring this idea to life, reproducibility was the crucial aspect for basically anything in scientific research. And I hadn't really thought about it like that. And to successfully make an impact for all and to implement something on a global scale, it must be reproducible. And this kind of takes me to a few lessons that summarize my learnings at Sunnybrook. So now I would like to go through a couple of key lessons I've learned working in scientific research for my brief period of time. So to start off, number one, challenge is bound when working in biotech. So although I was really only dabbling in a small part of a far more complex biotech project, I can say that you're just gonna face challenges no matter what you're doing, no matter how, whatever you're working in when it comes to really anything, but especially in scientific research. And for me, I can give you an example of a little bit of a problem that I faced at the start, which was not really having nearly close enough to the amount of knowledge I required in regards to university level physics, math, and biology. And I can say that being part of a very supportive team and being open to the idea of just learning whatever I have to as I kind of move along my project, figuring it out along the way, really helped with that. And that, no matter how knowledgeable you even are, there's going to be things that you just don't know because it's such an evolving field. And that I think, again, having that open mindset and embracing new knowledge with open arms is really what makes it a rewarding and very interesting. Number two, reproducibility is key in scientific research. In a world where there's only greater need for improved consistency and validation in research, reproducibility is fundamental. From learning about its role in research, I came to understand that it's just more than a list of instructions of how you did something. It requires in-depth documentation of methodology, data collection, data usage, as well as an account for all potential variables and conditions that occurred in a project. And the alteration of a single detail could change the results and prove a lack of reliability in something. And I can say that the introduction of tools for sharing records for peer review and collaboration is essential in this area. And it's where being exposed to key reproducibility applications such as Binder and Eurolibra, which both I hadn't heard of before this project, plays a major role in simplifying this kind of process of peer review. Number three, MRI research and development has revolutionized and is revolutionizing medicine. As someone who went into this internship with little to kind of no knowledge of the growing area of MRI research and development for treatment, I realized its impact in medicine is not only advancing imaging, but is widening the scope for treatment to a variety of conditions. And I can say that its non-invasive, non-radiation based approach makes it safer, and the impeccable quality of tissue contrast in comparison to other systems like X-ray systems really kind of help achieve that goal of accurate diagnostics. And watching MR technologists navigate through software and generate these detailed images allowed me to see the application of this technology. Finally, I just want to say I am so grateful to the Sunnybrook team, especially Dr. Graham Wright, for this amazing opportunity, and my manager Bonnie, who brought this experience to life, as well as Kelvin for an awesome first day. And last but not least, thank you so much to Mojan, Calder, Jay, Terrence, as well as Moses for just being such dedicated and really cool lab members. I enjoyed learning about every single project that you're doing, and you made this experience more remarkable than any. And just seeing your own passion for the area of interest, I was reminded of the goal of scientific innovation and scientific research, which is improving lives. So I gotta say, thank you so much.